Welcome to my presentation in the International Web Conference on Advanced Research in Science, Humanities and Social Sciences organized by MBB University. I thank the organizer for inviting me to present some of my work in this conference. Title of today's presentation: Organo-clay hybrid film suitable for optical memory switching and sensing applications. Now, what is clay? Clay minerals represent an important group of layered inorganic solid materials. They swell in aqueous dispersion into single sheet with thickness 1 nanometer and diameter 1 to 2 micrometer. They have colloidal size, high cation exchange capacities, large surface areas, surface reactivities, adsorptive properties, high viscosity and transparency. The property of intercalation, that is simultaneous incorporation of polar and ionic molecules as well as neutral molecules into the interlamellar spaces of clay layers, provide a potential for the development of novel functional organic inorganic hybrid materials. Now, basic building blocks of clay minerals are silica tetrahedrons SiO4 and alumina octahedrons. Silica tetrahedrons, its structure is like this, schematically this like this, and the silica tetrahedron repeat unit, they join together and form silica sheet. Similarly, alumina octahedron AlO6 structure is like this, they join together to form alumina sheet, and this ion molecule they form sheets, that is silica sheet or alumina sheet, then sheet upon sheet, layer upon layer, crystal, and layering silica and alumina sheets together results in different clay. For example, if one silica and one alumina layer together, then we call it TO type clay. Similar to two silica layer, one alumina layer is TOT type clay. This is schematically shown: silica tetrahedron, alumina octahedron, again silica tetrahedron. So this is a layer and this is TOT type clay, and this is a sheet, this is again sheet, this is again sheet, and as a whole it's a layer, and layer upon layer it forms crystal. Our works on organoclay hybrid films, we are interested to explore new organoclay hybrid nanomaterials with different functionalities such as sensing, biosensing, catalysis, optics, electronics, memory applications, and to study the organization of clay particles, adsorbed molecules, also study fluorescence resonance energy transfer between organic dyes in presence of clay, understand the process of hybrid nanofilm formations involving clay and organic materials, and also designing some supramolecular systems so that it can has unique applications. These are some related works published recently. Again, these are some works published. These are on organization of clay and dyes in organoclay hybrid systems. Now, why organoclay thin films? The planarity of the pi conjugated system of the confined organic molecules is increased, which extends the pi conjugation length. Also, the fluorescence quantum yield of the dyes is enhanced due to the suppression of vibrational motion of the confined molecules within the organonuclear systems. A clay mineral can accommodate a high density of organic molecules in its interlayer space without aggregations. The gallery height of clay layer can be manipulated through drying and swelling, that is wetting. Also, the organization of organic molecules can be manipulated with ease to control the properties of organic materials. Therefore, organic molecules confined in clay organic hybrid systems often exhibit unique, interesting electronic properties that are not observed in their solution or crystalline states. There exist two levels of organizations in such organonuclear hybrid systems. Number one, the organization of clay particles and organic molecules in the films, and the organization of organic molecules adsorbed on the clay surface. This is shown in this cartoon. This is clay, this is dye, and you can see the organization of clay and dye on the film, and again organization of dyes on the clay. So if this organization of these two types can be controlled or manipulated accordingly, property, electronic optical property changes, so it's possible to have interesting properties from systems. Now, organonuclear hybrid films for preparation, we used several techniques. One important technique is Langmuir-Blodgett techniques. This is computer controlled LB film deposition systems. This is another systems with fluorescence imaging microscope facility. Here again same LB film information systems using Brewster angle microscope facility, imaging facility. In this LB technique, we spread the solution of the molecule. We are interested to prepare the films on the water in the trough of the LB machine, and we allow the solvent to evaporate. Then we compress the barrier using computer, and once the molecule come closer, then we deposit in this manner. It is shown here. Now, organo-clay hybrid film formation, what we do normally in the LV trough, we filled up clay dispersion, and in the interface we spread the desired cations, and we allow some times so that the organic clay material come in touch with the floating molecules, and they form attached with the floating molecules due to cation exchange reaction or electrostatic interaction, because clay particles are negatively charged, and normally we use this organic material as cationic, and you can see here it's almost all molecules are attached with the clay, and here we deposited, and this attachment or interaction between clay and organic dye is a time dependent process, and this can be monitored using in situ infrared refraction absorption spectroscopy setup. Here it's like this, and here there is a light source, and if allow the light through a mirror to fall on the surface of the floating layer, then reflected beam is received through monochromator. So if with the thickness of the floating layer, it's possible to increase the intensity of the vibration within the particular vibration within the molecule in the floating layer. So one can have idea about the interaction. Similarly, it can one can have idea about the floating systems or reaction systems through imaging, and in that case one can use AFM or FSM, and here one has to deposit the films at different times and image, and one can see the difference, and both these instruments are already available in our departments, and this is you can see the plot of intensity of silicon oxygen vibration intensity measured through IRRS, and with time initially it is increasing and then it become flat. That means all clay, initially number of clay in the coming in the surface is increasing, but after a particular time it's become flat, that has been saturated. Similarly here also this is another clay. Similarly through AFM you can see this is image of a film taken after 5 minutes, these are 30 minutes, here concentration is higher, so one can say that interaction, one can have idea about the interaction through this process. This is some representative images, different types of clay, saponite, leponite, Wyoming, hectorite. You can see the thickness of the order of 1 to 2 nanometer. So it's a natural nanomaterials. Another process is self-standing process where we use filtration systems. We have filtrations and we use vacuum pump to suck the solvent from vacuum to make it vacuum from here, and in these systems we have a cellulose membrane, we use it here, and then we put the dispersion and dye at desired concentration here, and we suck the air, so it's become filtered and film form in this membrane. We take out the membrane, we can peel out the film on any desired substrate in this way for characterizations or applications. Here one example, we have studied a pyridinium derivative, structure is like that, and we prepared the films using self-standing systems. Interesting thing is that you can see the images. This line shows the image taken for organonuclear hybrid films at prepared at different concentrations just after preparations, and this line we put some DMSO in the film and then images, and this is under visible light, this is ordinary condition, you can see no color change, but when we expose this swollen or wet film under UV light you can see the color change, but in ordinary light you cannot see the color change. So to have idea why this color change, we studied some spectroscopy, and you can see this is for the SP paired films, the fluorescence spectra with monomer peak at 485 nanometer. In swollen case, you can see the peak shifted at 588 to 600 nanometer, and broad structural lens band occur. And this is normally characteristics of excimer formations. And to confirm this thing, what we did, we measure the lifetime of the both the peak monomer as well as proposed excimer, and we can see that this 588 nanometer band have 18 times longer than lifetime than the monomer fluorescence, and this give idea that this is due to excimer formation. And excimer is normally stacking of more than one molecule, one ground state and other excited state molecule, so it's some kind of aggregate. And we also, to confirm further, studied the XRD, and here we see the gallery height become the or spacing between layer sheets become double in the swollen state. You see in dry or SPR shape 48.48 nanometer, in swollen 0.93, almost double. And this gives a probability that two molecules can form pi-pi stacking, resulting excimer formation and showing the shifting of fluorescence band. And since it is a fluorescence or excited state phenomena, so its color change is observed only under UV exposure. This is the freshly prepared film. This is swollen under UV. This is again what we did. We once it is swollen, we washed the film and taken the DMSO out and dried, and you can see the color returned back. And this is a reversible process, and we have observed this up to say 50-60 cycles, and it's reversible. And here you can see in case of monomer, in dried condition the gapping is very less, so one molecule remain flat. In swollen state, gap is higher, so more than one molecule they form excimer. Accordingly, this fluorescence band shifting occurred. And this is a solvent independent phenomena. We have checked with water, chloroform and other solvent also. However, we prefer DMSO because this has high boiling point and it's easy to work in ambient conditions. And we propose one application of such film. This is freshly prepared films, and we wrote TU using a hearing bird just dip in DMSO, and under normal light, even after writing, if you observe, you cannot see any writing. But when you just expose this film, swollen written film under UV, you can see this one TU. Again, after washing, you can see this one. So we propose that it can be used as secret writing because you can write through wetting, but you cannot see it. Only when you expose it under UV, you can see it. Similarly, we can study the color switching for another molecule. It's indolil derivative. This is freshly prepared film. This is dried and heated film. This is swollen. And we have observed that this color change between this red and yellow is reversible. And you can see this is for different concentrations. This is no color as prepared freshly, dried red, and swollen is yellow. And this is a reversible process. And the reason is that normally the molecule remain confined within the clay layer. However, when it is heated, so pi conjugation system is extended, again color is become maximum flat, color changes occur. But when it is swollen, the clay layer gap increases and molecule become indolil ring become twisted, and certain disturbance of conjugation occurred. Accordingly, color change occurred. This is confirmed through XRD measurement. We can see SP paired film, you can see 0.636. However, in dried condition, it's 0.538. So maximum flattening occur, accordingly red color. But here you can see after swelling 0.85 nanometer increases and twisting occur, so yellow color. This is another example. It's a clay and polydiacetylene polymer films, and we propose the application for alcohol sensor. It's interesting. You can see the PDA has two phases. One is diacetylene monomer. However, when you expose it under UV, you can see they polymerize and they form a blue phase with typical absorption spectra like this. And this phase has almost no fluorescence. However, when you further expose it under UV or temperature or any kind of external perturbation, you can see the red phase, where absorption spectra is like this, and you see it has strong fluorescence. So we prepared a film using a dye, PDA, and clay, and this is just image of an film under this blue phase. And when we expose this film under alcohol, you see film after 5 times of puff after 1 hour of consumption of 2 peg alcohol, you can see this color change. And this color change again, you can see film after 5 times of puff after 4 hours of consumption of 2 peg alcohol. So it's interesting, just by observing the color change you can have idea whether a people has consumed alcohol or not. Similarly, we have studied the influence of clay on second harmonic generation. Second harmonic generation, it's a nonlinear phenomena, and it's a non-central symmetric system related issue, and to have this phenomena you have to organize molecule in non-central symmetric systems using LB technique. If you prepare J aggregates, then this J aggregate system is non-central symmetric in multi-layer, and you can have in monolayer, and you can have the second harmonic generation from this film. So this is the typical cartoon for showing J aggregation. You can see the single layer, it's non-centrosymmetric. If you just draw a center here, you can see in both sides it's not symmetric. But if it is two layer, then you can see it's symmetric. This one similar, this one. So it's symmetric. So monolayer or single layer in J aggregate in LB film is non-symmetric, and you can have this nonlinear phenomena. And here we studied this. These are some J aggregate conformation. But interesting rule of clay is that this one is intensity of second harmonic signal in presence of clay. This is in absence of clay, measured with time. You can see with time the intensity decreases in absence of clay, but in presence of clay it's almost stable. Here also same thing, but it's for it's with day. You can see even after 7-8 days in presence of clay, intensity almost parallel to the time axis, that is stable. Similarly, with temperature we have measured, you can see in presence of clay it's more stable. Here the just for idea, you see this black one is freshly prepared films. This is after 7 days. The SHG second harmonic signal intensity, you can see it decreases. But here in presence of clay, you can see the freshly prepared black one and red one is after 7 days, and you see almost no significant decays observed, so it's become very stable. Similarly, here also another example where we have shown that in presence of clay, the second harmonic intensity is very much higher than in absence of clay. So clay has interesting rule. Similarly, we studied energy transfer between organic molecules in presence of clay. In case of energy transfer, what we normally happen, it's an excited state electrodynamic phenomena where one molecule, say D, took energy from the directly to the source, and it transfer a portion or the whole energy to another molecule A, and the molecule A fluoresces through emission of photon. And this energy transfer extent depends on distance between the two molecules, relative orientations, transition dipole moments of the acceptor, as well as spectral overlap between the absorption spectra of acceptor and fluorescence spectra of donor. If presence of any external agent affects these factors, accordingly energy transfer efficiency also changes. Therefore, it is possible to sense the presence of external agent by observing the change in energy transfer efficiency, and it can be used to design sensors. So these are Jablonski diagram for energy transfer. So we studied using two molecules. One is NK thiocyanine derivative, another is rudamine in presence of clay. It's already published. Interestingly, you can see in absence of clay, energy transfer efficiency is 64.2%, but in presence of clay, it becomes 97.7%. So this is very interesting. This is mainly due to the fact that in presence of clay, the distance between the molecules decreases. You see 8.36, which was in absence of clay 13.4. Similarly, we studied energy transfer between another two molecules, acrylfluorine and rhodamine V, and you can see in absence of clay, energy transfer efficiency was 11.37%, but in presence of clay, it is 78.17%, almost 7 times increase. So, and based on this energy transfer, we have in presence of clay, we have designed several sensors: cholesterol sensors, arsenic sensor, hard water sensor, ion sensor, pH sensor, DNA sensor, Hg+2 sensor, etc. Therefore, in conclusion, we can say that clay materials are very promising for preparing organoclay hybrid supramolecular structure. Controlling the organization in such films may lead to maximization of properties such as colorimetric switching, freight, J aggregation, second harmonic generation, nonlinear optical effect, etc. And this kind of films are very promising for future technological applications such as optical memory, colorimetric sensor, optical switching, nonlinear optical application, etc. So I acknowledge my co-workers, my students, funding agency, DST, DAE, CSIR, my collaborators from my departments, other departments of this university and other university in India and abroad. These are some recognitions working in clay hybrid systems. For any query, future communications, you can please visit my website. You can email me at these email addresses, and you can have details of my publications in my website. So please do visit websites, and you are always feel free to interact with me through any communications. Thank you very much for your patience and listening, and hope in future when this pandemic is over, there will be a scope where we will interact physically in a thank you again. Thank you very much.